Hello, I am Dylan, and this is work with Lars Pedersen. I'll be presenting an overview of GOGMA, Globally Optimal Gaussian Mixture Alignment. So finding the transformations that best align multiple point sets is a critical task for many applications, such as finding absolute or relative sensor pose, or merging partial scans. Local optimization techniques for point set registration, such as iterative closest point, can be susceptible to missing correspondences and local minima. Missing correspondences can lead to incorrect data association, and without a good initialization, optimization can get trapped in local minima. Gaussian mixture alignment mitigates these problems by eschewing explicit correspondences and using a robust cost function. The transformation that aligns the Gaussian mixtures is the transformation that aligns the point sets if the point sets are well represented by the mixtures. However, GMA cannot guarantee global optimality and requires a good initialization to avoid local minima. Existing globally optimal registration algorithms use branch and bound to avoid local minima, but assume translation or correspondences are known. The exception is GoICP from Yang et al. 2013 and 16, which instead inherits the non-robust ICP cost function. In this work, we present GOGMA, the first globally optimal Gaussian mixture alignment algorithm with a natural application to rigid 3D point set registration. It uses branch and bound to find the global minimum of the Gaussian mixture alignment objective function and is therefore globally optimal. It also inherits the L2 density distance of the objective function from GMA and is therefore robust to missing correspondences from occlusion or partial overlap. The domain to be branched is that of 3D motions. 3 degrees of freedom come from translation, parameterized as vectors within a bounded cube, and the remaining 3 degrees of freedom come from rotation, parameterized as angle axis vectors within a solid radius pi ball. The 6D hypercube domain is branched using a hyperoctree data structure. Here we see the uncertainty region induced by a hypercube on a point X. The transformed point may lie anywhere in the uncertainty region, which is the Minkowski sum of the umbrella-shaped region, rotation uncertainty region, and the cubic translation uncertainty region. Our bounds use the spherical cap and the sphere which contain these regions. The geometric intuition for the bounds neglecting translation is that the upper bound is related to the distance to any point on the spherical cap, and the lower bound is related to the minimum distance to the spherical cap. This is equal to the radial distance to the sphere if the point Y lies within the rotation cone defined by the current branch of the domain. Alternatively, if the point lies outside the rotation cone, the minimum distance is to the edge of the spherical cap. This pairwise lower bound is a tight bound, and the gap between it and the upper bound converges to 0. The algorithm itself applies branch and bound with depth-first search and terminates with epsilon optimality. It finds the upper and lower bounds simultaneously on the GPU and integrates local GMA to accelerate convergence. Please come to poster 42 for more details and results.